That is a machine learning application running on the internet at a public address you can send to anybody. It takes a customer's details, tells you the probability that they are about to leave, puts them in a risk band, and explains which factors drove the decision. It was built from a messy comma-separated file that you and I first opened in Part 4. Today we build the whole thing, end to end, and put it online. And along the way, I'm going to teach you the one step that almost every beginner course skips, the step that turns a model that loses money into a model that makes it. This is Part 8, the Capstone. I'm Rohan Singh, this is CloudNimbus, and this is the one where everything ships. Before a single line of code, we do the thing that separates professionals from hobbyists. We ask what the model is for. Our telecoms company has 7,043 customers on file, and 1,869 of them left. If losing a customer costs the business £500 in lifetime value, that's roughly £934,000 walking out of the door. Now, we are not going to stop all of it. Nobody does. But suppose the model helps retention improve by 5 percentage points. On this customer base, that's about 352 customers saved a year, call it £176,000. Hold on to that framing because it changes what we optimize for. We are not building an oracle that knows the future. We are building a ranking machine, something that tells a retention team of limited size which 20 people to phone this morning. That is a much more modest goal and a much more achievable one. Right, 7 steps, and you've met every one of them already. Step 1, load and clean. The file comes down from the internet in one line. And there's our old friend from Part 4, total charges arriving as text rather than numbers, because 11 brand new customers have a blank space where a bill should be. We convert to numeric, coerce the blanks to missing, and fill them with 0, because a customer who has never been billed has genuinely paid nothing. We drop the customer ID, because an identifier is not a feature. It's a label with no meaning, and feeding it to a model is a classic way to fool yourself. Step 2, split honestly. Train and test, stratified so both halves carry the same proportion of churners. Same sealed envelope you learned in Part 1. Step 3, one pipeline. Column transformer, one hot encoding for the categorical columns, scaling and imputation for the numeric ones, and a classifier on the end. One object. It remembers every transformation and applies it in the right order to the right data, which, as you learned in Part 6, is what stops leakage before it starts. Step 4, compare. We fit 4 models through the same pipeline and lay them out side by side. Not just accuracy on its own lies, and Part 5 showed you exactly how. Gradient boosting, 80.6% accuracy, precision 67.4, recall 52.4, and an ROCAUC of 0.843. Logistic regression, right behind it, 80.6, 65.7, 55.9, and 0.842. Random forest, 77.6% accuracy, and a plain decision tree trailing at 72.9, with an ROCAUC of 0.657. 2 things worth noticing. The first is how close the top 2 are, a fraction of a point apart. The second is that logistic regression, a technique from the 19th century that fits in a single line, is competitive with modern gradient boosting on this problem. That happens far more often than beginners expect. Reach for the simple thing first, always. Step 5, tune the winner. Grid search CV, cross-validated, tries every combination honestly. It settles on a learning rate of 0.05, a maximum depth of 2, and 200 trees, reaching a cross-validated ROCAUC of 0.849. And here is where most courses stop. They print the accuracy, they say well done, and they roll the credits. We're not going to do that, because at this exact moment, our model loses money. Every classifier we have built gives you a probability. 0.82 means I think there's an 82% chance this customer leaves. But to turn a probability into a decision, something has to draw a line, and by default, every library on Earth draws it at 0.5. Nobody chose that. It's a convention, and it is almost never the right business answer. Watch what happens if we accept it. At a threshold of 0.5, our model has precision of 66% and recall of 50%. It catches half the levers. Now put money on it. A retention call costs £5 and a lost customer costs 500. Run that across the 1,409 customers in our test set, and the model produces a net result of minus £1,415. It is worse than useless. It costs more than it saves. So we slide the line, drop the threshold to 0.3, and the model now flags 538 customers out of 1,409, about 38% of the book. Precision falls to 53%, meaning roughly half the people we phone were never going to leave. That sounds worse. But recall jumps to 76.5%. We now catch 3/4 of the customers who were actually about to walk. And the money, £96,310, positive, against minus 1,415 at the default. £97,725 of difference from changing one number. Compare it to doing nothing at all, which on this test set costs £187,000 in lost customers, and the model is worth £283,000. That is the lesson of the entire series compressed into one decision. The maths was never the hard part. Knowing what you're optimizing for, that's the job. A wasted phone call costs £5. A lost customer costs 500. So of course you should accept 100 wasted calls to save one customer, and of course the default threshold is wrong. The library couldn't know that. Only you know that. Step 6. Interpret. Ask the model what it's actually using, exactly as we did with the penguins in part 1. Top of the list, and it isn't close, being on a month-to-month contract at 35.5% of the model's attention. Then tenure, how long they've been a customer at 17%. Then fiber optic internet at 12%. Then no online security and no tech support. Read that as a sentence because you can. New customers on rolling contracts with fiber and no support add-ons leave. That is a retention strategy written by a machine from a spreadsheet. You could hand that to a marketing director this afternoon and they would know what to do with it. Step 7. Save it. One line with JobLib and the entire fitted pipeline, every encoder, every scaler, the trained model, all of it, goes into a single file. Then we load that file in a fresh session and score one new customer to prove it survived the journey. That file is your model, not the notebook. The notebook is how you built it. The file is the thing you ship. Now we leave the notebook, because notebooks are for thinking and files are for shipping. Train.py reproduces the entire training run from the command line and writes out the model file and a metrics file. That matters more than it sounds. It means anybody, including you in 6 months, can rebuild your result from nothing with one command. App.py is about 40 lines of Gradio. Gradio is a library that turns a Python function into a web interface. You describe the inputs, contract type, tenure, monthly charges, and so on. You point it at your saved model, and it builds the page for you. No HTML, no JavaScript, no web development. Run it, and there's the application from the top of the video. Let's give it a genuinely risky customer, 2 months tenure, month-to-month contract, fiber optic, no tech support, high monthly charges. 70.5% probability, high risk, and there are the reasons. Now a loyal one, long tenure, 2-year contract, modest bill, 2.5%. No risk factors flagged. It works. And notice the model didn't change at all between those 2 clicks. You built a thing that thinks about customers it has never met. And then you deploy it. The deploy file walks you through it step by step. For free, on Hugging Face Spaces, create a space, upload 3 files, wait 90 seconds. You get a public URL. That URL goes in your CV, in your portfolio, and in the first line of your next job application. And I want to be clear about why this step matters so much, because it's easy to dismiss as a nice extra. Nearly every beginner portfolio is a folder of notebooks. Notebooks are private, they need explaining, and a recruiter will not run one. A link that a stranger can open and click is a completely different object. It says, "I can finish things." That sentence is worth more than another model in a notebook. Before we finish, 3 honest things about what happens after deployment, because a course that stops at "it works on my laptop" has told you half the story. 1. Models go stale. Yours learn the customer behavior of one particular period. Contracts change, competitors launch, prices move, and quietly, month by month, your model gets worse at a world that no longer matches its training data. The professional response isn't cleverness, it's a calendar. Measure the live performance and retrain on fresh data on a schedule. 2. The threshold we chose is a business decision, not a permanent truth. If the retention team's capacity halves, or a saved customer turns out to be worth £200 rather than 500, the right threshold moves. Write down the assumptions you used, the £5, the 500, next to the model. Anyone who inherits it needs to know what you assumed, not just what you built. 3. A model that predicts people carries obligations. Ours decides who gets a retention call and implicitly who gets offered a discount. Check whether it behaves differently for groups of customers in ways you can't justify, and be ready to explain any decision it makes to the person it was made about. The algorithm said so is not an answer, and increasingly it isn't a legal one either. So, you started this series not knowing what the difference was between AI and a chatbot. Let's count what you actually have. 6 trained models. A real 7,000-row business dataset that you cleaned yourself, including a dirty column that would have silently broken everything. A gradient descent loop you wrote by hand. A neural network, a tuned pipeline, and a deployed application with a public link. That is not a beginner's portfolio. That is a junior data scientist's portfolio. 3 things to do next, in this order. First, do this whole project again on different data without me. Pick something you actually care about: house prices, football results, your own bank statements. Everything you learn transfers. Only the column names change. Nothing consolidates knowledge like the second time through. Second, go deeper on the part that gripped you. If it was the maths, study linear algebra and statistics properly now. You'll find they finally make sense, because you've seen what they're for. If it was the engineering, learn Docker, APIs, and how models get served at scale. If it was language models, build a proper retrieval system over documents you care about. Third, write about what you built. A short post explaining the threshold decision we made today will teach you more than another tutorial, and it's the single most underrated thing a beginner can do. One last thing, and I mean this. In 12 years of building cloud systems and teaching close to 1,000 people, the ones who made it were never the ones with the best maths. They were the ones who kept a small project moving every day when it wasn't working yet. That's the whole trick. It is not talent. It's sitting down again. Everything from these 8 parts is linked below, all 8 notebooks, the Capstone project, the student handbook, the glossary, the cheat sheets, and the 30-day plan. Subscribe to the channel for the deeper dives that follow this series. And if you want the guided path with graded exercises and support, the full course is on Udemy through CloudNimbus. Send me your deployed link. I read them all. I'm Rohan Singh. This has been AI and Machine Learning from Absolute Zero, brought to you by CloudNimbus. Now go and build the second one.